I was telling you about fault testing. Okay. So, test generation. So, I had told you that you have a list of faults. So, generate the list of faults, then do fault compaction. Okay, so update F, then random pattern generation. Then I had told you that fault simulate the random vectors. And let us say FR is a list of faults that they generate, right. So, we can go and remove all those all those faults that are caught by the random vectors, right. Then we pick a fault G from F, then generate a test T for G, then fault simulate T, okay, and let us say it results in Ft. Okay. So, remove F equals F minus T, then check has F become equal to 0. If it is not, then go back, and then if it has become, then stop. Okay. So, this is what I had explained to you, but based on what I just told you, right, I may have redundant faults in my circuit, and as a result, unfortunately, I may not have a situation where the list will become 0, right. I may have untestable faults. So, there could be untestable faults, okay, due to which I can never bring down the list F to 0. So, we have to be aware of this, right, and during test generation, suppose the tool can prove that there is no test, then it will classify it as an undetectable fault. Okay. When we say generate a test T for G, maybe we realize that G may not be testable at all. So, G could be untestable, because it may be a redundant fault or whatever be the reason, right. So, we have to remove T, I am sorry, we have to remove G, okay, and say it is a untestable fault. Okay. So, if that is the case, then remove G. Okay. So, if G is untestable, remove G and then continue. So, your ATPG tool will be able to tell, hey, I had undetectable faults. They may be redundant, etc. So, I cannot detect those. Then, as I explained to you earlier, in the process of generating the test T or G, if it is going to use backtracking, okay, then it may take a lot of time. It tries so many combinations, none of them is working out, keeps on trying, keeps on trying. It may take too long for doing this backtracking. So, we may also have a situation where if G is taking too long, okay, that means generation of test is taking too long. So, I should have written that way. If generating T is taking too long, drop G, okay, and then proceed here. So, such a fault is called as aborted faults. So, these are aborted faults. So, sometimes I may end up having faults for which the tool is unable to generate a test because it just takes too long, not because it is redundant. And finally, of course, there are some faults which are actually testable. So, suppose I had 100 faults, okay, and it turns out that about 2 of them are undetectable, and let us say 3 of them are aborted. So, I have 95 guys which are testable, and I was able to find vectors. Then I say fault coverage is equal to 95 by 100 or 95%. Okay. We may not be able to get 100% fault coverage. That is the basic thing all of you have to appreciate. Okay. We may not be able to get 100% coverage because there may be undetectable faults, and there could be faults which take so long to generate tests that we give up. Okay. There may be other reasons for undetectable faults. See, here is another example. So, there may be somebody who has designed a circuit like this. He took a block B1 and block B2, okay, and this block B1 generates many outputs, and this output was not important. So, he just left it open, he did not connect it to any output. Okay. These are the primary inputs and these are the primary outputs. So, if there are such wires, okay, you cannot find many faults which can be propagated to this. For example, stuck-at faults at these points cannot be found. Okay. So, stuck-at faults here cannot be detected. In fact, faults that can be propagated only to these lines cannot be detected. Okay. If I can propagate the faults to this line, good, I can go ahead and detect it. But if there are some faults which are only going to get propagated to these outputs, then I cannot detect those. This is a very common thing that happens in circuits, right? I mean, we make use of pre-built circuits. I may have acquired this circuit from an outside vendor. That circuit produces a lot of outputs, but for my purpose I do not need these outputs at all. So, I do not connect them, that results in some undetectable faults. Another thing could happen, right. I may have block B1, block B2, I connect all these guys, and there may be some inputs I do not need them. So, sometimes people tend to ground them or connect it to logic 1 and things like that. Okay. Because when I use B2, it is only these inputs that matter to me, the others are not important, but I can't leave them hanging. So, I ground them or something like that. An example could be, see, maybe I have a 3 input XOR gate. I do not have a 2 input XOR gate. So, I am using a 3 input XOR gate. So, I can go ahead and ground this. Okay. So, this will act as a 2 input XOR gate. The same is true with AND gates. If I connect this 2 by 1, it will act as a dot B. If there are such things happening in the circuit, then you will realize that the stuck at 0 fault here cannot be detected. Because there is no way I can activate such a fault. Similarly, a stuck at 1 here cannot be detected. Right. So, as a result, when people tie, these are called ties. Okay. This is called tie. We tie a value or a wire to a 0 or a 1. Okay. So, if somebody has used these ties, so in fact, there are what are called as tie cells, which are used to tie a particular net to a 0 or a 1. If you have these tie 0 or tie 1, which are helping me in connecting a wire to a logic 0 or a logic 1, ground or VDD, then those faults cannot be detected. Okay. So, you will realize that the fault coverage, okay, fault coverage is the total faults modeled that means the list of all the faults that I considered, total faults caught multiplied by 100. So, in case there is a very good chance that it will not be 100%, because I may have redundancies, I may have aborted faults, and I may have tie cells and things like that. Okay. So, our ATPG tool will tell me the reason. Okay. It will classify the faults into aborted, undetectable, and of course, these are the faults that are actually caught. So, this is what contributes to fault coverage. So, in the industry, we should be able to explain why certain faults cannot be caught. Okay. We can't do much about this, right, but we should be able to explain why these faults cannot be detected, but there may be something that we can do about aborted faults. Okay. So, if you join the industry in the test role, right, and you are asked to generate test vectors, the expectation is that you may have to reach some high number like 95%, 96%, 98%, etc. So, this is a target. Okay. We do understand that some small percentage of faults cannot be detected. So, you should be able to explain why you are not able to get 100%. And if people are convinced that indeed that is not possible to get 100%, they will accept your answer. But people will challenge you, hey, why are there so many aborted faults? What are you doing about them? Okay. So, one obvious thing you can do is you can increase that time that a ATPG tool takes to detect the fault. You can say, I will allow the tool more time. It will take a long time. Okay. Some of these tools may take hours and hours to generate test vectors. So, you may be willing to generate test vectors by adding, by allowing the tool to take longer. So, that may help you to improve it by some small percentage. So, what was 95 may become 95.5. Okay. So, that is how it works. People try to struggle and get that extra 0.5%, 0.5%, 0.2%, etc.